All right, hello and welcome back to another lecture here for organic chemistry. We are following up with chapter 3, where we're talking about acids and bases. So we're going to start by talking about the two important definitions of acids and bases that are relevant to organic chemistry, specifically Bronsted-Lowry definition, and then we'll talk about the Lewis definition of acids and bases. Make sure that you follow up with our sample exercise packet as well. Again, we'll be doing those separately in another video, but it's good to have those on hand while we talk through the lecture. So very briefly, we're going to review the definition, starting with the Bronsted-Lowry definition of acids and bases. And remember, Bronsted-Lowry definition defines acids and bases based on protons. So it kind of follows the proton. The acid is what donates a proton in a chemical reaction, and then the base is what accepts the proton in that acid-base chemical reaction. So like, for example, when you take hydrochloric acid, like as a gas, for example, and you put it into water, the hydrogen is donated from the hydrochloric acid to the water molecule. So it's donated by HCl, so that means HCl is the acid, and it's accepted by water. Water is acting as the base. And then what you have is you form a conjugate base. That's what's left over in the chemical reaction. And the conjugate acid, that's basically, if you look at the reverse reaction, in this case, this is a bad example because here, this reverse reaction actually doesn't occur. We know HCl is a strong acid, so it's going to strongly favor the products in this case. However, if we just kind of imagine, you can imagine the hydronium ion here donating a proton to chloride. Chloride then acting as a base in the reverse reaction, so we call it the conjugate base. The hydronium ion acting as the acid in the reverse reaction, that's our conjugate acid. I hope that makes sense. Yeah, so again, and this just restates that basically. The conjugate acid is what happens when the base accepts the proton, so the base becomes the conjugate acid, and likewise the acid in the forward reaction, so in the reactants of the forward reaction, becomes the conjugate base. So just as an example, why don't you go ahead, pause the video, look through this reaction here, and label the acid, base, and conjugate acid and conjugate base here. And then we'll do it together. So I'll go ahead and give you a pause. Okay, so hopefully you restarted the video now, and let's go ahead and go through this and see which one's the acid, base, and then the conjugate acid and conjugate base. So here, this is called the tert butoxide ion. You don't know that quite yet, but this is going to be what it's called. It's reacting with water. I hope you know that one by now. And what we're seeing is this water has this red proton here in the reactants. And then in the products, that proton is given up by the water. It becomes a hydroxide ion, and it's transferred to the T-butoxide ion, which becomes T-butanol or T-butyl alcohol. So clearly what's happening is a proton is transferring from the water to the tert butoxide ion. So the thing that gives up the proton, that's what's called the acid. So water acts as the acid here. The thing that accepts the proton is the base, that's the tert butoxide ion. Now, if we imagine the reverse reaction here, the hydroxide ion is going to pick up a proton. So in the reverse reaction, hydroxide would act as the base. So this is the conjugate base. Likewise, the T-butanol will act as a acid because it's going to give up a proton to the hydroxide ion. Just kind of reviewing these definitions here with the first lecture of chapter 3. That brings us to sample exercise number 1. Go ahead, get out your PDF. We're going to go through these as well in a supplemental video, but this is like a good time to go ahead, pause this video and do this sample exercise and then figure out what your acid, base, conjugate acid, conjugate base are. We're going to be using these terms frequently throughout the semester, so it's good to just get started. Okay, and then we're going to finish up by talking about Lewis acids and Lewis bases. So the Lewis acid-base definition is something that becomes extremely important in organic chemistry. First, we have a lot of proton transfers in organic chemistry. So we see a lot of Bronsted-Lowry acid-base mechanisms, but all of the reactions that we do, we're going to follow the transfer of electrons from one species to another. So almost all the time, we're going to have a Lewis acid and a Lewis base. But let's review those definitions first before we kind of get too far into the weeds here. You'll notice I skipped ahead in terms of sections on the chapter. This is section 3.9, comes at the end of the chapter, but it's just its own small section. And I thought we might as well get it out of the way while we're talking about the definitions of acids and bases. So first up, the Lewis acid, we changed the definition. Now we're not focusing on the transfer of a proton. Instead, we're looking at the transfer of an electron pair. So a Lewis acid accepts the electron pair, and a Lewis base donates an electron pair. The way I always remember this is that you have acid accepts. So the acid accepts a pair of electrons is the best way to remember that. Keep in mind this Lewis definition is actually expansive, so it includes everything from the Bronsted-Lowry definition. So acids that are Bronsted-Lowry acids are also Lewis acids. Bases that are Bronsted-Lowry bases are also Lewis bases. So like, for example, this is the one that we showed you at the beginning with hydrochloric acid. I already mentioned this is a bad example, but we can keep using it here. Here what we have is we have water donating an electron pair to the proton and picking up this proton to become the hydronium ion. So water donates an electron pair, therefore it is acting as the Lewis base. On the other hand, this chlorine is accepting a pair of electrons from the water, from the proton. So that means that it is actually accepting a pair, so it is acting as the Lewis acid. Now it's important to note that while Lewis acids and bases are, Bronsted-Lowry acids and bases are Lewis acids and bases, it's not true the reverse. So some Lewis acids and bases are not Bronsted-Lowry acid bases. And this basically happens when there's no proton transfer, right? Bronsted-Lowry acid-base reactions require a proton transfer. That's not the case with Lewis acids and bases. So for example, if you take water and you react it with boron trifluoride, you can form this adduct here. Now this is not a proton transfer, so neither of these are Bronsted-Lowry acids or bases. However, they do fit the Lewis definition, because here we have this water, the oxygen in water, giving up a lone pair, it's donating a lone pair, and this boron in boron trifluoride is accepting that lone pair. So here, this is your lone pair donor, so it's the Lewis base. This is the lone pair acceptor. This is the Lewis acid. And then over here in the products, we have just one molecule that's the result of this combination. We call this the adduct. So just keep that in mind. This is called the adduct here. Okay, and then if you skip to the end of your sample exercise packet, sample exercise number 10, that's where you can kind of follow through with identifying the Lewis acid and Lewis base for each of these. That does it for the acid-base definitions. We'll go ahead and pick up when we talk about some more important aspects of acid-base chemistry with organic chemistry in the next lecture.